to be here. Particularly, it's the second lecture in probability I ever gave, in philosophy, as a formal lecture, actually the third now. I made a statement that I'd rather be a janitor in a philosophy department than a tenured professor at Harvard Business School. That was my aim. And I'd rather, of course, be doing probability, studying probability in a cafe than hotshot at Davos. And I pretty much have fulfilled this because I guess I'm getting close to become janitor in a philosophy department, which is which I find vastly more honorable and enlightening than being hotshot at Davos or professor and thing. And I have only one interest: the problems of probability. So let me, we discussed it. I think one of the persons I've learned the most from, by the way, are you hearing well? Is it okay? It's not too loud? Okay. Is Paul, because I had, when I finished The Black Swan, I had a conversation with him, and then I meditated for 2 years and came back and finished it 2 years later, and we'll see what the conversation is about, concerning the notion of probability, which is his specialty, being a philosopher. The second thing I learned from him is that there are some arguments you don't need empirical support for. You should be able, being a philosopher is being able to figure out from a chair, from your armchair, what is wrong with the world, and being able to predict events. So we're going to mostly work on that, how we can predict the crises, or the continuation of the crisis, what can happen, simply using a priori arguments, or with minimal empirical arguments. But now let's look at what are the mistakes people use with probability. I will start with the turkey problem, which is probably one of the oldest problems in science. It's an application of problem of induction, with a twist of what I call moral hazard. The second one, illusion of measurability, cognitive issues we have when we think we measure something. Domain differences, something I call Mediocristan, Extremistan, which makes actually life much easier. What I call the Casanova problem. And then bias making computation on balance. Why we underestimate small probability. Why there's a typical bias in underestimation of small probability coming from model error. Why model error goes one way, not the other. That's pretty much my talk. As we discussed it, I'm going to have the 15, 20 minutes of sort of more literary talk, and then I'll get a little more technical. See, so you can bear with me. And then in the end, I'll become, more literary again. No, it's okay with you guys. Raise your hands if I get too technical. We had, luckily, a model error here, but visibly my computer doesn't work. So I'm going to have to maneuver with slides, which is fun because you can show the fragility of technology, that gains in efficiency always come with increases in fragility. So let me start with the turkey problem. In a black swan, there's a very simple, a turkey is fed for 1,000 days by a butcher. And every day confirms to the turkey statistical department, because that the butcher loves turkeys with increased statistical confidence. And then they have a department, and everything, if you apply everything technically possible in a book of how you do inference, statistical inference, every day will increase the confidence in that statement, that butcher loves turkeys, all right? BLT, or butcher loves turkeys. There's a statement, and you compute a P, and you can have scientific papers, people agreeing, disagreeing, but they all say that additional information increases their comfort with that statement. And then there's a day in the United States called Thanksgiving. And on that day, it's never a good idea to be a turkey, all right? So you're going to have a surprise revision of belief on a part of a turkey. So this is what the classical problem of induction is linked to that, we'll see. But with 2 or 3 things we can figure out here already. Number one is that event was a surprise to the turkey. Was it a surprise to the butcher? Okay? Was it a surprise to the butcher? No. So the whole idea is how not to be a turkey. Okay? We're going to figure out how not to be a turkey. It's very simple. Okay. And the second thing is that when I wrote my book, The Black Swan, I started facing people telling me, is this event a black swan? But an event depends on the observer. For a turkey, something can be a black swan, but it won't be for the butcher, you see? So there's no universal black swan. And then it would ask me, is September 11 a black swan? Black swan being that event that lies outside what you can expect can happen. Well, for someone flying a plane into a tower, okay, the event is very predictable. For the other one, for the people in a tower, visibly, it was unpredicted, okay? So you can say that the judgment of probability is always very subjective, depends on point of view. And effectively, there's a disease that have been studied a lot by a lot of thinkers and a lot of cognitive scientists. It's called the autism spectrum, in which people can be of high functioning intelligence, but be unable to recurse or unable to impart to others opinions different than the one they have themselves, okay? And I think that there was this big problem that I already discovered, that sometimes with the rise of scientificization of things, the rise of the internet, the rise of people who like to work with formulas, at the same time, you have the loss of what we call theory of mind, so that people can understand that other people have other different, that probability is not something very hard that exists, that's observed, that everybody knows it's the same thing, you see? It's relative to an observer, a given observer. So this is the turkey, the first one, then it's the turkey problem. Now, an argument that has been always, since I had hair, I started, trading options very, very young, and we're going to see what I encountered. I had hair, and people would tell me I was obsessive about some class of rare events by saying, I don't want to be turkey about these events. And people kept countering me with the argument, every time I cross the street, I have a small probability of risk of dying. How can I cross the street? I tried to explain why it's not the same thing, and it took me about 10 years to figure it out. That I'm not telling you don't cross the street, I'm telling you don't cross the street blindfolded. And it's very different, okay? Between facing a small probability that's rather computable of rare event of a car running you over, and it's not the end of the world because your whole gene pool won't disappear, and the other one is putting, these folds on your head and then crossing the street. And of course, you saw what happened in the crisis. We had blindfolds. So first, let's talk about measurement of risk. Many of you, I'm sure, work in finance, and many of you hear of things called risk measurement. And we discovered, my co-author and I, Dan Goldstein, that that people didn't understand what risk measure was, okay, because of something called framing. And that giving people a risk measure, they have the illusion that you can measure risk like I'm measuring the stable, you see? Measuring the stable is subject to some measurement error. There's a complete qualitative difference between measuring this and measuring some event that hasn't happened in the future, okay? Something you can observe and something. So people use the same word measure that completely distorts their behavior. So if you tell someone, I measure this risk versus I estimate the incidence of future events to be so and so, they act completely differently. And so there are a lot of framing problems with probability, particularly rare events. For example, if we supply people with the following packages, you tell them on average you're going to lose 100% of your money every 30 years. 65%, 68% invest in such a package. This, you see, but if you tell them you have 3.3% probability of losing all your money in any given year, a very small probability to do that. And it's the same with plane rides and everything, okay? So the way you phrase things, so we are not, we're very influenced with what we call the ecology of a problem, how it's phrased. So when you address something with measurement, automatically people start taking a lot of risk, thinking some expert measured probability. Like you land in Abu Dhabi and they tell you temperature is 31.3 and the probability of a Libyan disaster has rose from 3.1 to 3.23, the past 2 hours. And then the stock market went down in China by 1%. So you see that it's the same thing. It's not the same qualitative item, but and that was my conversation with Professor Bogosian 3 years ago, where and about using the same term to describe two different operations is non-trivial, okay? It's not rigorous philosophically, and of course it has some cognitive impact. So we tested a lot of these by showing that if you give someone value at risk and tell them it's random, they're going to take a lot more risk. And just simply because of the way we're suckers for measurement. And of course, German judges, you can roll the die before sentencing. You're going to produce long sentences when the die is high, when the numbers are high, and short sentences when numbers are low. So humans are not very good in handling numbers. There's something about, there's some classes of behavioral distortion that stem from using measurements, and probability is a big one. So let me now say the war I had and continue a debate I had with this gentleman. At some point about 3 years ago, when the Black Swan came out, I had more hate mail than I thought a human being can get them, and as I got so used to them, I started missing them. You know, on days like you wake up, you go downstairs, open your computer. I used to open my computer, hoping to get, some whatever invitation to a nice party the same day or something exciting. I used to get hate mail and enjoy it. So I got a lot of hate mail from quants. Includes the gentleman here wanted to debate me by saying, well, you're against the Gaussian. I'm not against the Gaussian. It's like being against a hammer, all right? It's like I'm against using a hammer in brain surgery, but I'm not against using a hammer in carpentry, all right? So he wanted to debate me. But luckily, before the debate, he went on the record. Some events had happened in the summer of 2007, in August 2007. And he was cited. Incidentally, he worked for a firm called Lehman Brothers, which explained why we only had one debate. The second scheduled debate never took place, all right? But there's one important thing. He said, what happened, the event we saw that summer of 2007 should have happened every 10,000 years, okay? Which is fine. But I said, look at his picture. He doesn't look 10,000 years old, okay? He doesn't look, if you can see. So I'm glad the Wall Street Journal provided us with this picture. Very nice. But now we have two things. So how do you derive small probabilities? Where do you get them from? You see? Where do you get them from? Either you get them from some prior belief about small probabilities, or you get them from observation. You agree? If you're getting from observation, you can't get 1 in 10,000 years from observations. You can't. So unless, but that's a tragedy. If you're getting them, if you're fitting empirically probabilities without a model, without anything, okay, small events are going to be necessarily rare, no? So if I take the relative error of that probability, for example, if I can't talk about the 100-year flood if I have 5 years of data, you agree? All right, so when probability P is smaller than 1 over n, then you got an infinite relative probability error, okay? That's the first thing. The second one is, well, now the smaller the probability, the less you observe it, the more you have to use some theory to produce it, you agree? Whatever theory you want to call it, or, laws of whatever, okay, to produce this probability. But the higher, but the problem is, the smaller the probability, the higher the impact. That 5-year flood is more damaging than a 1-day flood. You agree? And the 100-year flood is more damaging than a 5-year flood. So the smaller the probability, the worse the event associated with it. So this pair, probability times magnitude of the event, becomes more and more stochastic as probability becomes small. And that is the tragedy of small probability, and we're going to show it now, that the smaller the probability, the less we know about it. Much about it. That's one. So this is the two tragedies that are raised in his statement: is that empirically it doesn't work, and theoretically you need more and more theory. And then, of course, we're going to see now small calibrations blow up small probabilities. So even if you have the theory right, the model right, small measurement error blow up small probabilities. And there are also some errors, what I call them meta errors on parametric measurements. So. But what helps us is the following. It so happens that we're lucky and that there are two domains. Two domains that are rather distinct. The first one I call Mediocristan. For those of you who want a learned name, I call it the central limit theorem works in real time. And the second one I call Extremistan. Another central limit either doesn't work or it works in a billion years when, the dust settles, and we'll see what happens when they have a billion years when they finish a new building of NYUAD, Abu Dhabi and stuff like that, right? So I mean, in the future. So this is the distinction, and let me give you the intuition of the distinction. Okay. The first domain, the thought experiment I used in the book The Black Swan, is I said I gather 1,000 people randomly from the population of the world. Okay. And I bring them to Abu Dhabi. We give them visas at the border, right? And then you put them on a scale, and you add to that sample the largest possible human you can find, all right? How much of the total would that person represent? How much? Let's work it out. The average is 160 pounds, say, in America, but of course you'll have lighter people, and you'll find someone, all right? From New York, probably, or well-fed. You add it, so maybe if the person is 4 times the average, you're likely to have about 40 basis points for that person. You have 1,000, 40 basis points for the maximum, okay? And as you go from 1,000 to 10,000, that maximum is expected to be what? 4 basis points, you see? 4 basis point is 0.04%. So we're talking peanuts. So as your sample becomes larger, not a single observation can mess up your total. You agree? Well, everything you've learned in business school, have been in business school. I'm not talking in math because in math they're sophisticated, but in business schools, and I went to business school, so I can make fun of business school people. So in business school, they teach you everything is based on that. Well, it sort of doesn't work in business. It works in other domain. It works sometimes in casinos. It works but you can't drink in the streets in Abu Dhabi. But if you random walk, there's something called the random walk theory. You give someone, see what happens. You give him every day some liquor and see how he gets drunk where he gets. Well, that works, okay? It works in some physical field, but not all right? Now, let's play the same thought experiment, the same people. Again, you're going to have people from China, India. Expected net worth of these people is going to be about what? $500,000? Okay, you have a sample of 1,000 from the population. I know you work it out, but it's not much. I mean, it's much, it's a lot, all right? Total net worth. You add to that sample, now not the heaviest human on the planet, but the richest. The Lebanese guy, it may happen that he may be the same, by the way, incidentally. Okay, it may be good for a thought experiment to have the same person play both roles. So the guy is, how much is he worth? $60 billion? So he will be 100%. Plus or minus rounding error. And if you move your sample, all right, if you increase your sample, he still will be 100%, okay, from 1,000 to 10,000. So these are 2 domains. One I call Mediocristan because it's the collective impact of the regular that determines the properties. And the second one, the exception, plays a disproportionate role in determining the properties, all right? So these are the 2 domains, rather distinct. And there is convergence to one domain, or non-convergence to that domain, that's quite clear, visible, and you can work it out, and you can work it out, okay? For example, there's something called central limit, as I was explaining. If you start adding up things drawn from certain classes distribution, it becomes Gaussian, the bell shape, all right? But others become Gaussian, but at much lower rate. Sometimes you don't know the rate. So this is sort of like these 2 things. But these make our life very easy, okay? Because the impact of rare events is small in Mediocristan. Rare events happen. Now here, if I take the average height here, we're about what, 150 people, okay? You bring in someone, no matter how tall he is, not going to budge much the average. You agree? We're pretty much safe. You can't change. Even if you brought someone from New York, you know how crazy they are. It's not 7 foot. A basketball player won't change anything. So rare events. But now in finance, everything is rare events. Welcome to Extremistan. I figured that out when I started trading options. And this is, if you trade between 1990 and 2007, 1 day variation in a portfolio that traded interest rates derivatives in the UK would have represented close to 100% of your total return, no matter what you did the rest of the time. Okay? Things are determined by the extreme. Take the book business, okay? This is derivative portfolio, where it's compounded. One good thing about trading derivatives is everything with derivatives is compounded. All the small mistakes compound, you see? The same thing happens with leverage, of course. But leverage is linear, derivatives are nonlinear. So you have, you can start seeing defects, okay? Then I realized that all the models couldn't work because if everything came from the exception. I sort of was lucky that I was a trader in 1987 when I had hair, and I discovered that property, all right? In 86, I discovered that property, and of course the stock market crash of 1987 represented most of, okay, so. Now I've outlined the problem, that if you're using tools made for Mediocristan, in Mediocristan, good for you, all right? That's fine. Provided you can prove, you have to have a conversation with Professor Bogosian to see if you're rigorous about the way you have ascertained that you are in Mediocristan. You agree? But then if you're using tools from Mediocristan, using them in Extremistan, you're getting, you see my problem with the measure, you're going to take a lot more risk. Even if someone told you it doesn't work, you're going to take a lot more risk. You're going to get in trouble, things are going to be fragilized. I'll add later the notion of moral hazard. Moral hazard is someone is taking advantage of the misperception, statistical misperception of the system by society. Okay, we're going to talk about that. It's like you make bonuses because you get paid. You're an Extremistan, you get paid on a yearly basis for something that blows up every 10 years. Okay, well, visibly. And then when the thing blows up, you don't give your money back. So we're going to have a lot of risks like that in the system because that's how people are paid. This is another way to look at Mediocristan, Extremistan. This is how the variations are. These two have exactly the same volatility. You see these two shapes? Same standard deviation, same volatility, but look how one is. One you always have rain, like being in London. The other one's rain in Saudi Arabia. I was in Riyadh the day when it rained, all right? But boy, did it rain, all right? It's like a flood. So it doesn't rain. It's like it floods every 40 years. I don't know how, for 2.5 hours, that's about it, all right? So I think the extreme would be to get, so that every 10,000 years it rains, you know, and that's once, and that's it. So the thing is, there's so many socioeconomic variables in that class, not even funny. Take any socioeconomic variable. I know now book sales because I'm an author, okay? So you look at the properties of winner take all and among authors, and you see that everything's driven by bestsellers. If you have 1 million manuscripts in a market of books, 1 million of people who call themselves authors, in the fiction area, but that fiction will also include, of course, Tony Blair's memoirs, of course. But fiction, he's a member here, no? No, it's the other guy, all right. Fiction, Greenspan's memoir, definitely. So you have, in the fiction area, you have 1 million novels in the market. People usually work for Starbucks. Out of 1 million novels, 20 will be sold by publishers every year. Out of these, how many would represent half the sales, therefore 90-some% of the returns? How many do you think? Sorry? 11. Who says, and some other number? 27. One, no, but it hasn't happened, but it's possible. So, but this is the okay, so give me two things. You're all right. It's between 5 and 35, okay? And it's so unstable. That's going to be my discussion. If we knew how large the rare event, what the role of the rare event, everybody would be happy. The problem is there's no stability to it. You see? Next, I'll talk about it. But one thing I want to stress here is that almost everything get this, concentration, and then, of course, lumpiness. We call it fat tails. Okay? Let me show you something about why I had to fight, for this incidentally, fallacy of volatility. Things, when you fatten the tail of a process, make it lumpier, you see less volatility, but when it moves, boy, it moves. You see? So people mistake it for lack of volatility, and particularly that's something the US government is very good at being fooled by, all right? That's a profession. But now, is anybody here, let me use one mathematical concept. Is anybody here a mathematician or a statistician or someone who studied? There is a word for how much something departs from normality. In other words, how much we are away from Extremistan. In other words, how big the role of a rare event plays in data. There's one measure, no? What is it? No, standard deviation tells you how much volatile something is. Sorry? Outliers is something outside the data. There's a measure that you can have it on Excel. No, variance is how much something moves. Sorry? No, there's a measure. It starts with a K. I'm helping you. Curtosis, all right? Curtosis is the forced moment, tells you how volatile your measurement of a second moment is. In other words, it tells you how much you depart from the Gaussian. You agree? Excess kurtosis is you get on Excel. You put data, you put excess kurtosis, and it gives you that number. Okay? So when I started, everybody thought that, yeah, it's true that we have fat tails, in the sense departure from Gaussian. We're not in Mediocristan. But we know how to measure that effect. And effectively, someone got that Nobel went for accidental reason using a metric that usually captured that. But in fact, doesn't work outside his computer, right? No, so and let me show you what I did, all right? I took every economic variable I could find. Okay, initially I stole them, and then later on I had to pay for it because, you know, okay. By taking whatever I could find that had a lot of data points, typically 10,000 data points, okay? And measured the contribution of the largest observation to kurtosis, you see? So, shocking result. Something like sometimes there's a silver for daily variation. One observation represents 95% of the kurtosis for the last 40 years. 1 day in 40 years represents 95% of the kurtosis. Silver. Stock market, the crash of 87 represents 80% of the kurtosis of the last 40 years. Okay? So what does it tell me? If I have 40 years of data, and then 1 day in 40 years represents so much, it means you don't know what kurtosis is. You don't have a stable measure of it, you see? It either means, as I believe, and someone told me Jean Bouchot was here, that it doesn't exist, or equivalently, that you cannot use any form of Mediocristan plus adjustment for your as a tool, okay? Now, meanwhile, this we have known since, with this formality, with this level of formality since the crash of 87. Anybody equipped with a computer and blessed with no knowledge of business school portfolio theories was aware of that, okay? The problem is I don't really know, okay, another few things about kurtosis. Here they're ranked: silver, yen, crude oil. I'm saying all the big economic variables. And of course, temporal instability. This is if I measure yearly kurtosis for oil. Look how unstable it is. And all of them have the same property. Plus, there's another thing, is that if I start summing data, instead of taking daily return, I take monthly return, yearly return, that kurtosis would drop. No, actually, very often it increases. Okay? So it means that you cannot use, there's no Mediocristan, or the tools linked to normality are unusable. So I said we need to ban some terms from application to economic life. If you ascertain that you're not in Mediocristan and you don't have a good reason for it, standard deviation, variance, correlation, regression, least square errors, all these need to be. You cannot use them. There's no basic, from the things, you cannot use them, all right? So if someone is using them, he's definitely going to be measuring something random. Effectively, it is random. Out of sample, it doesn't predict itself. It is random. Now, I am not saying we cannot use statistical theory. It works beautifully on a lot of things. We're going to see where it works. If there's a domain, for example, take my caloric consumption, okay? How many calories do you consume a year? Sorry? Who said 400,000? 800,000, all right? Tonight, how many calories? Say you're going to have a meal, all right? How many calories are you going to have tonight? Can you have? How many? Okay, but say you want to splurge tonight because I heard the reception. They're going to serve us the best food possible in Abu Dhabi here. That's what Professor Bogosian informed me before coming. All right, say you're going to splurge, all right? Okay, say you go to 4,000. Before, more than that, there's a level at which you die. So no, not a single day is going to change your weight much, which is a good news if you want to splurge, but bad news if you want to lose weight, which we all encounter. It's a collective impact of everything, you see. So there are domains in which you could use these tools, but you can't use them in finance because there can be a day that can change your net worth markedly, you agree? And my whole story is that when I was a trader, the first thing I went to be a pit trader, and they told me, come over here. There's an old trader. I said, come. Joe over there. I said, yes. He said, come, kiddo, because I was a newcomer. I said, yes. I had the hair, you understand. He said, he over there. I said, yes. He said, he made 7 million, which was a lot of money at the time, in 7 years, and lost them all in 7 seconds. I said, okay. I said, now you can go, all right? So that was, so you understand that there are two different probabilistic structure. I'm not saying now that we've solved the problem of statistics of probability. I'm saying at least of eliminating some areas in which it's not that acute. You get the idea? So these problems are more acute. Now we're going to talk about Hume in a minute, but say all these problems are vastly more acute in one domain than another. You see? This is what I'm talking. You cannot, once you ascertain Mediocristan, Extremistan, then you cannot predict with any form of precision, acceptable precision. You cannot use these terms. And the small probabilities are incomputable and play a very large role. Let me continue with that, with that problem. Hume's problem is, this is a Turkey problem again. If I have 1,000 days time series, of course, you ask one of my students who study financial engineering to measure this, and they'll tell you all tests confirm. And of course, the time series go to 0 on 1,000th day, right? As in a Turkey problem. So let's see now, using classical statistical methods, everything in sight that you could use, what can the past tell you about the future, okay? And that's what I call Hume's revenge. Visibly, the gentleman here, after a period of nothing happening, declared that it was a great moderation. He didn't realize it was an increase in fat tails. The gentleman here went to Congress and said, it never happened in the past, okay? And then, as if past events had to have a predecessor. And effectively, I made the test that large deviations don't have predecessors. Small probabilities, large shocks don't have predecessors. If I have all the data up to period t, okay? I plug all the data, try to get information about outlier. And I get what happens, t plus 1, I get a complete cloud. In other words, past outliers don't visually, you can see it, cannot help you. I'm talking here about 30,000 pieces of data, right? If you take up to history, period t, you take a history of how many people died in war up until the first war, it doesn't help you predict the outlier of the first war, okay? Well, you do the same with financial data, with economic data, same thing. Inflation numbers, pre-Weimar, you get the idea. So I'm saying that the mere fact that something has not happened in the past means nothing about non-occurrence in the future, and you can see it. Yet people still calibrate to the past, like the Obama administration looking for unemployment data from the past, which is nice for entertainment, but if you keep running it out of sample, you see that it doesn't predict outliers. However, normal events seem to predict themselves, okay? And sampling theory seems to work. You cannot justify it inductively, of course, but sampling theory seems to work, okay, without too many accidents. So here, we don't even need to be philosophical or anything. You see a very clear error of reasoning. Someone telling Mr. Greenspan telling Congress people, these events never happened before, so therefore it's okay, we didn't make a mistake. And not a single congressman told him, but Mr. Greenspan, you never died before. Okay, it doesn't mean you're immortal, you see. So you get the idea. He didn't realize this. This is why we have some domain specificity to these type of errors. That in a natural domain, we tend to not make these errors. When it comes to domains that are artificial, like finance, we tend to make these errors. So anyway, so continuing with this, with this. Okay, we looked at what possible, what we call a generator of a time series. Now this, I'm getting mathematical, so you're going to suffer a little bit, I'm sorry. And then it gets better, all right? We looked at an exhaustive set of generators of time series that could have produced the data for the first time in 1,000 years. You agree? Okay. The problem is you don't observe these generators, okay? These numbers are produced by the generator. You just see the numbers. You don't see the equation. You know, in a real world, I don't know if many of you are aware, you don't observe equations. What do you observe? Data. That's all you observe, sorry. That's all you observe is data, right? So, it can be, if a data is a Bernoulli, that's what we call a generator, then the thing you see very quickly, the properties, it's fine, okay? If it's Gaussian, then you see the properties. You end up seeing the properties with some error. Then you're sort of fine. If the process is Gaussian plus some series of jumps, okay, then I'm sorry, you have a problem, okay? Because you don't know how fast you're going to see the properties of the time series, okay, assuming stability and all of that. And finally, if it's unbounded, say something like Cauchy distribution, you will never, okay, unless you know it's Cauchy or you fit it using log scale, you don't read the data. In other words, you can be easily fooled by generator. Something that delivers, as I showed there, something that delivers very normal Mediocristan with once in a while things going wild with jumps, okay? You cannot reverse engineer that. And it's literally impossible to fully reverse engineer. I can always fool you into, so here I'm saying, given that you don't observe, and this is a set, with this you cover everything. Actually, there's a theorem that this one covers everything. I mean, you can do this one plus this one because they converge. It covers the something called Duffy-Pan-Singleton, how you can re-express everything through diffusion plus jump, they call it. Okay? So, and a series of jumps, and each jump has its own distribution. So what I'm saying is that I wrote that with someone, and nobody could understand what we're talking about. Is that, and I tried to revoice my series with the story of the ice cube. Okay, it's very easy for anyone to predict if I put ice cube here how it's going to melt. You agree? So you see, you can project what water is going to be produced by the ice cube. Okay, this is called, the forward, arrow, all right? But then if you're the backward arrow, it's not easy. If I see water on the floor, I don't know what it came from, you see? It can be this ice cube of that shape, this shape, maybe no ice cube, maybe just water. So going from the water to the reconstruction of the possible ice cubes, you have a lot more degrees of freedom than going from an ice cube to what water is going to generate. You see my point? So going from probability distribution to data is easy from a generator, if you write it down. Much easier than going from data to what possible generator. You could be fooled permanently. Now this is critical because there's a lot of economic literature that was written called something on Bayesian. You've heard of Father Bayes and what would, okay, so there's a panacea that could tell you a lot. And Professor Bogosian is the first person I encountered who said, well, it makes no sense. It requires some assumption that agreed on. No, it requires some restrictions. So let me give you a very simple restriction. You're observing data. The theory is as follows. You're observing data, I'm observing data. We have different parameters, different priors, called priors, okay? As we observe the same data, we'll end up converging, okay? You see? To have the same, but the problem is that it presupposes that both of us have the same probability distribution. If I think the probability of the third kind, and you think it's the second kind, no matter how much you're going to observe, I will still say, oh, this jump is possible, and you will say this jump is ruled out. Okay, this is sort of an extension to the Turkey problem. And that is a tremendous mistake that was not pointed out in all this literature on something called rational expectations. How agents, update data communally, how, There are a lot of things in use of Bayesian methods that people don't understand how much restrictions we are putting on a process to be able to perform these methods. I'm not saying these methods are wrong. I'm saying don't make the data tell you more than it can tell you, you see. And data does not tell you much. For Hume, there's no basis, okay, to extrapolate, to extend from the observed to the unobserved. Okay. Here I'm saying the case can be milder because there are a lot of situations. Actually, there's a solution that's harder to shift the problem into not taking some classes of risk which expose you to blow-ups. But we have to live with that problem. We need to live. You cannot do statistics without being concerned with the severe problem of induction. We have to live with the fact that there's no hard reason, call it hard, whatever you want to call it, no scientific, no hard reason to go from this data that you've observed to the properties that you haven't observed the data okay. Now, which brings me to two sets of people. And let me exactly explain what happened and why you have two sets of people, all right? And why sort of the crisis happened. If I engage in a strategy betting against rare events, small probabilities are, to me, unknown. But if everybody's betting, it has the same payoff. And actually, almost all financial institutions have the same payoff. I make a bet, I go sell an out-of-the-money option, all right? You don't have to figure out which one. These options have 1% probability of losing money any given month. That's how they're priced. So it could be 1%, 2%, who cares, all right? You get a bonus. There's something on Wall Street called a bonus you get every year end. You agree? Okay, you get a bonus every year end. So I don't really care. I don't really care about my expected payoff. I care about what I say, time to pants, to being caught with pants down. So this is a New York expression. I'll make it a little more formal. Time to being caught, all right? So what you want is you don't really care of the expected value of the package. You want to maximize the number of bonuses. How do you maximize the number of bonuses? By making bets on rare events. You get the idea? So the banking system, I wrote in The Black Swan in 1982, in 1 month, in one summer, lost more money than made ever in the history of money center banking. All right? But then managers collected, of course, compensation before. Bonuses were not big. The government bailed them out and said, one loss, who cares? It's nothing, all right? Then they did it again on a bigger scale. And now the banking system, again, in 91, from real estate, and people don't know about the RTC and how many companies disappeared, lost more than ever before. Of course, they said, it's nothing, extraordinary circumstances. And then they did it again, okay? But now think about it. If you are, the best thing is to play that game it's called the moral hazard argument. Bob Rubin from Citibank, all right? I call it the Rubin hazard. Made $100 million in bonuses from Citibank, all right? Citibank went bust. Okay, he said it was unexpected. He wrote a book on uncertainty, by the way, all right? He said it was unexpected. He kept his bonus. He didn't pay it back, you see? So, but effectively, you have school teachers, all these people through their taxes are paying it, or savers through inflation are paying it, through the bailouts. So this is the moral hazard argument. And you can see the moral hazard pervading when people don't have a payoff, the upside without downside, okay? They go into hiding risk where it can hide the best. And no regulation can ever do anything to do that. My rule is to have liabilities. Say the captain goes down with a ship to eliminate it, because no regulation can help with this. These guys can play all the games you want. And this effectively moral hazard shows in this fact, very simple fact. The stock market, what were the returns, you think, last 10 years in the stock market in America? Sorry? No, negative. Since 2000, about $5 trillion were lost in the stock market. Because remember that companies issued, compared to funding, people issued stocks way above here. Okay, people kept buying every month way above here. So the public has lost several $1 trillion in the stock market. Okay? Managers, on the other hand, made about $1 trillion in compensation. So this, you get the, you see that because you get a yearly bonus off of something that doesn't blow up every year. And of course, you supply Sharpe ratio, all these metrics to your investors saying, why you did the right thing. Now let me continue. And how much more time do I have? We started we started late. I have another 10 minutes? Okay. So let me continue with other biases. Well, there are two kind of payoffs. This I call the fragile payoff, and this I call the convex payoff, where effectively you're positioned to benefit from rare events. And it's very simple to distinguish between these two. Now there is another problem. Don't cross the river because on average 4 feet deep, that I've been working on now. Okay. What I call the convexity of the errors. Why we can't compute small probabilities? Because there's something called convexity of the error. All right. In other words, when the first state, earlier I said you cannot make a statement of probability without meta-probability. Okay, if you're estimating probabilities, you want to know your estimation error. Let me give you an idea of how that works. If someone tells me the probability of this event is 0, and I tell him, how do you know? He said, I know because I am a prophet. I know. Okay. This is entirely coherent and consistent, but perhaps unrealistic. You agree? All right. Now, if someone says the probability of this event is 0, and I tell him, how do you know? He said, I measured it. What is this? Where is the inconsistency there? Sorry, what is? No, aside from that, I'm saying there's another inconsistency. You say, I measured that probability, and I think it should be 0. Think about it. Yes? Sorry? No, aside from that, there's another problem, even simpler.
He's saying measure and think.
He said measure, and it said 0, all right? He said, I estimated the probability. Let's use a word, make it simpler. Say, I estimated the probability to be 0. How can you estimate something at 0? No, if you estimate something, it has to have estimation error. You agree? So therefore, you cannot have something worth 0 if you estimated it. You get the point? You cannot estimate something to be 0. 0 plus estimation error. You see? Plus allowance. So this is where the incoherence starts. And the more uncertainty you have about small probabilities, the more you have the small probability raised by that effect, by the estimation error. This is what I call meta-probability raises small probability. Okay? This is why Curtosis variance raises it. Now let me show you this in action on something very simple. Wall Street has a method of generating probability distribution and computing this tail. You agree? They measure this mass over here. They set the level K and then measure the mass below level K. Okay? And then you tell them, how do you measure this? Well, they say, well, we estimated sigma, the standard deviation of a Gaussian. Let's assume we are in a Gaussian world, all right? This is why I tell you, if you have uncertainty about sigma, you can't really talk about small probability, even in a Gaussian world. If the probability is estimated, look at what problem happens. So this measure off of a sigma, I measure this tail, okay? I measure this mass, which is the equation up there. Now, I'm going to compare two things. I'm measuring this, okay? Measure, all right? Off of sigma. Measure off of sigma. Or here, sigma minus 25%. I measure it plus measure off of sigma plus 25%. Okay, divided by 2. Okay, I compare these two numbers. You see what I'm doing? Is instead of measuring something at one, you usually find standard deviation, you plug it into your equation. You agree? But the standard deviation is measured. No, it has measurement error. So I say, okay, what's my measurement error? Well, about 25%. Okay, I'm going to measure this plus 25%, minus 25%, and average them. You see? Guess what the difference between these two measures become? What order of magnitude of error you're going to have on that? For 10 sigma, an event that happens 10 standard deviations away. Granted, it's small, but 10 sigma in finance or in economics is something so common, people don't even talk about it, all right? I ask people, they tell me, well, 20% error. No, 4 billion. For a 10 sigma event, you have 4 billion error in measurement of small probabilities. Okay? Here I'm going to the Bogosian territory where I'm sitting down in an armchair and I am deriving fragility in a system simply from listening to people, an argument, and seeing inconsistency, you see? The minute you measure something, you see, you have measurement error. You have to see if whatever function of that does. Okay, this is a little technical for people in the back, but it's the same concept of someone telling me probability is 0. I had to add to it that measurement error. It increases the small probabilities. Here it increases everything in the tails. It becomes explosive. So the error is bigger and bigger for small probabilities. In other words, even if you have a perfect model, but you have to estimate parameters, you have some standard error on parameters, you got to include that in a model. It makes a model blow up for small probabilities. Okay, so another way to show this, I call this convexity to measurement error. Well, effectively, it's based on a very simple concept, Jensen's inequality, which tells you don't use the average, don't cross a river that's on average 4 feet deep. In my new book on anti-fragility, my new argument, I'm taking this one step further. I do the following. You can't really go by average when you have a concave function. And the example I use is, I'm sure some of you have a grandmother, no? Okay, so we're looking at two propositions. Grandmother at 30 degrees, all right? You know, you put your grandmother at 30 degrees for 4 hours. For 4 hours. You put her in a nice chair and you give her, you know, coffee, all right? Whatever, okay? So, and you look at the effect on her health. Or now grandmother at minus 10 degrees for 2 hours. And at, what is, to make it 30 on average? And at 70 degrees, okay, at 70 degrees for 2 hours, okay? So on average, you have your grandmother at 30 degrees for 4 hours, okay? All right? What do you think what happens to your grandmother if you do this? Okay, you lose a grandmother, all right? Why is it so? Because the health of your grandmother is a concave function, okay? This is your health of your grandmother, and this is 30 degrees, and averaging minus 10 and 70 is not the same as taking 30. You agree? Well, it's the same thing in economics. When you say, well, it was on average, unemployment is on average going to be 10%, you see? Okay, you plug it in the equation. It's different from taking unemployment at 12% or taking the unemployment at 8% and averaging the GDP or averaging deficits, you see? So I call a concave function of a number, you see? So this is why we have that problem with probability. We have that problem everywhere in economics. It's absent. It's called second order effect. It's absent. Traders know it. It's don't cross the river if it's on average 4 feet deep, you see? But so the way, well, I mean, look at this is what the way people do regression in economics is they estimate a parameter, put in an equation, instead of re-putting the equation every time across all possible parameter estimates. It's a little technical, you see? But here, the way I work with it was probability. I think any function I'm using of that small probability, instead of averaging my estimate of small probability and putting it in there, I average the function across all the probabilities. Then I get different result. To write it in equation form, it's the only equation I'll write down, all right? I have f of, you estimate the parameter, sigma, okay, or it's different from, the difference between these two is monstrous for probability, okay? If you were to use that, then there's a second notion which is the error I have on a probability or distribution of that probability, because you can't say probability is 10% without giving distribution. Sometimes it's 10% and I can be very confident. Sometimes it's 10%, but I'm not confident. You have so this is what I call the meta-probability. If you introduce meta-probability, you raise all small probabilities. It's very strange. All small probabilities are raised. So this is sort of like an approach to the solution. Now, now we're still standing before the crisis, saying what am I doing with this? How to take this home? We're going to see what we do before the crisis, and we're going to see the solution now after the crisis. We have 4 minutes, 2 minutes. Before the crisis, you can say anyone building position, risk position, exposure to small probabilities, thinking they have computed them, okay, number one, are off. 2, overexposed. They're taking definitely more risks than they think they are because they're estimating something, all right, that cannot be estimated, okay? Sort of like what someone flying thinking he's seeing what's going on. In fact, he's not seeing as clearly as he thinks. And the second one is typically, but not always, you have an expectation of bias and estimation probability, okay? Now, what do we do with this? My solution is called the force quadrant, and I did it in this shape, okay? There are some position or some exposure I have in life that don't depend. Maybe I'll find the slide. I couldn't find it here. Technology, you see, is beautiful, huh? Where is that fourth quadrant? It disappeared. The computer swallowed my swallowed my slide. This is, these things happen, no? Okay, so I have to do it myself. If I'm making a bet with you that if there's a war, if there's a war, say between New Jersey and New York, whatever, okay, I win $1. And if there's no war, you win $1. You agree? You see? This is called a binary bet. This one I call type 1 bet exposure, okay? M1 exposure, actually, I call it, okay? And if I'm making that bet, now if I'm off on the probability, it doesn't cost me, it's not open-ended. My loss is not open-ended. If there's a war or not a war, I'll just pay $1, okay? Now, the type 2, called M1 plus, this is M0, sorry. I'm making bets on a zeroth moment of distribution. That's sort of more technically. The second one, so I'm clipping my exposure to the tails. From the payoff itself, organically, I'm clipping, you see? The second one, the second type of bet is open-ended. Okay, so we're making a bet that for every degree, or let's say war between New Jersey and New York, okay, for every bullet shot, you owe me $1, all right? So you have unlimited exposure, okay, particularly the aggressiveness of New Jersey people and New Yorkers. You see, you can have a lot of bullets, all right? So you get so this is one M0 bet, M2 plus bets. In other words, this one is bounded exposure. I call it bounded, and this one is unbounded exposure. And then you have, of course, type 1 distribution, type 2 distribution. This is Mediocristan, Extremistan. This one here is a quadrant to worry about. You all have unbounded exposures, and you are in Extremistan. You cannot use mathematics in this. When I first said that, in the first edition of the Black Swan, I had so much hate mail, it's incredible. But now what I did is I used this to tell people, you know what? All these philosophers, they speculate too much. Statistics work beautifully in these 3 quadrants. Guess what? They all got all excited. They actually start arguing with me, the other way. If you tell statistician, this is where your techniques work, all right? It's as insulting as telling them this is where techniques don't work, you see? But phrased that way, they get all excited. Oh, it's so good. Yeah, you're right. This is so good. All right. But the fourth quadrant is where the action is. Everything is here. Now, how do you exit the fourth quadrant? By bounding exposures. And actually, mathematically, then the moments become computable, and all this problem of convexity of error and small probabilities goes away. You see? You clip it. It's called clipping the tail. Now, how could it be in the fourth quadrant and exit it? There are a lot of mechanisms, okay? So in other words, you want to transform your exposure. Typically, in the fourth quadrant, you want your exposure to be transformed. Let me move away from these equations. to something, from something like this to something with a floor. You can't lose more than a certain amount. So then probabilities are very computable. And the example I give is I call it the barbell. I have two portfolios with equal measure of risk. This is my last sentence, incidentally. One is exposed to medium risk, but we don't know what risk means. The second one is 80% cash, all right, or whatever, inflation hedge, 20% maximum risk, all right. You see, they're both medium risk, but the second one doesn't care about any probability below 20% because it's convex, you see. Well, the first one is subjected to errors in computation or rare events. Now, there's one thing also I want to say before I finish. Let me take it out on portfolio theories. There's something about a gentleman called Markowitz, okay? He fell for this problem, okay? And let me tell you, when someone talks about estimate, he said the following. He said, this is mean variance, this is the theory. Okay, assume parameters are X. And then later on in the text, for which he got the Nobel Prize. Actually, that's from his paper, not the book. Okay. Then he says how you need to estimate them, not realizing that if you have to estimate these parameters, you blow up his whole theory. If you have to estimate the parameters, the whole theory blows up. He made exactly that error of someone saying, I estimated this to be 0. If you have to estimate parameters, then you have second-order terms to put in. If you put second-order terms in Markowitz mean variance allocation theory, it blows up. Okay? This is one of the inconsistencies. You can find it in an armchair. Thank you. I'm very honored to be here. Looks like the crowd was not too panicky over some of my technical things. Usually mathematicians even don't understand me because I use my own jargon, having operated on my own. Okay? But thank you for listening to me. I'm honored to be here. Yeah.
About 20 minutes for Q&A.
Okay. So I'll handle the Q&A. I thought you were going to filter them. So I prefer to keep this because I'll answer some questions with graphs. Hold on. Who was first? The gentleman in the back and then you, all right? The gentleman in the back here. Sorry? Yeah, here, yeah.
Hello. Hi. If the experts in the field have trouble grasping or agreeing with some of your thoughts, whether on a more technical level or more philosophical, how do you address the fact that the majority of the people with an average comprehension level of a high school 10th grader or 11th grader, how do you get the average person to understand and accept some of your contrarian kind of
This is a great question. The answer is Berlin, June 21. I hope you can make it, Paul. And let me tell you the answer. There's a professor, Gigerenzer, who does heuristics, work on heuristics. And you have two kinds of knowledge. Heuristic knowledge is knowledge embedded in practice, okay? In other words, you ride a bicycle? Okay, you ride a bicycle. Do you write down differential equations before you ride the bicycle, or you just ride it? All right. So the two kinds of knowledge. Knowledge grounded in practice, there's know-how, and there's know-what. Our know-how is very developed and has been through history. Our know-what is very limited. And when it comes to small probabilities, Professor Gigerenzer in Berlin has shown in several domains, and now we're merging because sort of like the messages fit like this, okay? That human beings are vastly better than experts at handling probability. And that's his point. Simply, for in a lot of things. And he calls them heuristics, fast and frugal rule of thumb heuristic that you have inherited from the environment. And if I take what I call rationalistic knowledge or propositional knowledge, here it is, what it contributes to modern life. And this is a body of heuristics, heuristic knowledge. Heuristic knowledge is rule of thumb. Like, for example, how do people hire a secretary? How do you get married? We have heuristics anti-this, anti-that? We have a wiring mechanism for risk detection and stuff like that that works rather well in some domains if you phrase probabilities the right way. And if you do something, people tend to, we are vastly smarter, okay, than our brain. You get the idea? So this is my answer. And effectively, for a lot of things, this is what, and I want, actually, I did something more interesting here. I'm going to give you the answer, and the answer is here. I wrote a paper with Espen Haag. I was an option trader for about 21 years, as I told you. From I had hair till I lost my hair and continued, all right? And we noticed the following, that option trading, you think options are derivatives, are a complex financial instrument that requires knowledge of probability, no? Okay? You would think that. Then how come in 1700 they traded using more sophisticated methods than after Black-Scholes? So we wrote that paper, option trade used very sophisticated heuristics, never the Black-Scholes-Merton formula. I'm talking about cab drivers in Chicago who would alternate between being option traders and cab drivers, depending on season. You see? They're illiterate, they price the option based on heuristic rule of thumb. So this is the answer. And this is how Professor Gigrenzer got excited when he saw this paper, because it gave him backing. We went through records of 1900 and the 1800s, how people traded options. And then we said that later on theory, there's something that we call lecturing birds how to fly. You lecture birds how to fly, then you say, give me the Nobel, look, the birds is flying, and I just lectured it. So they gave Black and Scholes the Nobel in 73. Then we realized we had vastly more developed heuristics and technique before 73, and Black-Scholes make you underestimate the risk of rare events, whereas traders did not. They were vastly more sophisticated in raising these, using my convexity argument. They used it from 1900, all right? And we have documents that used it in 1900, you see? But documented how you should, these events are, to be priced that way. So documented, and of course we see from practice and records of exchanges. So we went through history, the entire history. So this was finished about 7 years ago. We went through, I don't know, years of record searching, and it was published only now in the Economic Journal. So 7 years of hate mail we got, including from Mr. Merton, okay? Professor Merton, we got so much hate mail from him, and and then suddenly now it's published in the Economic Journal, all right? So this is the power of heuristics. So I hope I answered your question, that effectively we don't use probability that much outside casinos, classrooms, quantum mechanics, some fields, you see. Sorry, there was a second question in front of the gentleman, the second hand raised.
Hi, thanks. So I'm just curious, what are the implications that you think this has on the field of finance? I mean, it seems that it's quite negative.
Yeah. It's not that negative.
The second part is what are some other similar fields that people think we have this control or measurable quality about that we're mistaken about?
In finance, it's not that negative. And actually, I'm trying to go back to historical heuristics to see how people have handled financial risk and stuff like that. And people were very good with, for example, options. Anything that requires a computer to price, not an open pit, is not heuristic, and therefore we get in trouble with it. In finance, if you just install a law, if you lower debt, okay, there's something about debt that causes moral hazard. Or if you have a law, a very simple heuristic, captain goes down with the ship, all captains, all ships, then risk would vanish much faster than if you do regulations. Or in the other fields looked at by Gigrenzer, was other than finance, he has medicine. He uses this for medicine, but it has so little interest, okay, in medicine except to document human error, that for a long time going to a doctor was likely to triple your chance of death. No, actually it peaked in the 1900s. And then it's not till penicillin that the break even happened when you go see a doctor. Today, if you go see an economist, if a government uses an economist, it quintuple the chance of blowing up and stuff like that. So we're not there. So, but doctors, medicine uses heuristics, and that was Gigrenzer. Medicine uses heuristics. The minute people start using probability, they start making mistakes. Okay. The gentleman has a question here. So, yeah.
You're saying that we need to be using heuristic notion to regulate markets going forward?
No, there's something called less is more heuristic, in the sense that the richer the model, the more you have to, the more complex the regulation, the more people can go around it by hiring a good lawyer. And Goldman Sachs made money. I was a derivatives trader, and I tell you, we made money off of regulators because they make a complex regulation, and all you need is a good lawyer and coffee, and about 2-3 hours, and you find somewhere. The more complex the regulations, the more you find somewhere to create a product to go around it and arb it. So this is why less is more. No, we should use more heuristic, but not blind heuristics. But this is the approach. Is there's a way to look at the model needs to be parsimonious, robust in the sense that it doesn't work that well on your computer as much as it works in real life. The other models, they take you to the Nobel. They work better on your computer than real life and stuff like that. There are some rules of heuristics, but it's an entire new field that is very powerful, and we are much more sophisticated. For example, baseball players use a very sophisticated heuristic. It's called the gaze heuristic. You throw the ball, you look at the ball, okay? No, sorry. To catch a ball, you run by looking at a ball, and the angle while looking at a ball allows you to catch a ball. And it's very, 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 very technically sophisticated, but yet people discovered it by themselves.
Thank you, Mr. Taleb. Since, as you have said, our previous data doesn't give us the right clue about what will happen in the future, I have a question about financial crisis. Since we cannot trust economists, we can't trust statisticians, we can't trust politicians, what is our escape? I mean, should we trust ourselves? Right. Should we trust our wives?
Okay. When I wrote incidentally, I'm not saying you can't trust past data for one reason. Let me tell you one thing. I said there's masquerade problem. If the data shows fat tails, a fat tail distribution can masquerade as thin tails, but thin tail distribution cannot masquerade as fat tails. Okay, that's as a point aside. For maybe 2 or 3, we'll pick it up. We'll do something with it. It's not important to answer you. To answer you about the crises, I have my rule about natural systems. Okay. What is a system? Who is the best risk manager in history? Who is? Mother Nature. It's been around 3 billion years. That's better than Markowitz. All right. Okay. So, I'm trying to have great. So, Mother Nature has ways in which it handles risks of systems. All right. So I wrote something called that. Nobody understood immediately. It's taken a while. Even I didn't understand it immediately. It's 10 points for a black swan robust society. And actually, not tomorrow, but the day after tomorrow. The day after tomorrow, I'm presenting a version of it on 10 Downing. Is about what rules would be taken to prevent. And then the rules are as follows. 1 over n heuristic, which is actually in portfolio theory, fragilizes 1 over n heuristic robustifies. Okay, which is probability free in portfolio allocation. But something equivalent, and it says things you should fail fast, not late. Low debt in an economic system makes you less concave to projection errors. So debt fragilizes you. Debt is a measure of overconfidence, of underestimation of errors. So I have a recipe, but I would say if I were to say what society should look like, if you have low debt, then the financial system will be a lot more stable. Smaller company, more artisanal style, you'd have less growth, but it would be more robust growth. And things that people don't like, but eventually they're going to have to swallow it, all right? And I want things to break early, not break late. So the economic life should be modeled after the restaurant business, which is the best business in the world, particularly if you live in New York. You never have a restaurant crisis. You wake up and say, restaurants all went bust today. You don't have that, all right? They have their crisis early in their life, each one of them. They don't communally have that. They're all like artisan-style thing. They all have low debt. And and they're all driven by overconfidence of the entrepreneurs, unrealistic view of the future, which is very good for us consumers, all right? And for those who stay, they have some rule of thumb that make them stay for a long time. Particularly if you have clients who like to go, like me, for example, you go patronize them and overeat, right? So you see the restaurant business. So if you look at that as a model, and then you can see what other companies that have survived 200 years, 150 years, 100 years, 300 years. And then you realize they follow the law. There's actually a statistical law that follows what is called Lindy law that tells you that the life of a company, if a company has been around 10 years, its life expectancy conditionally is 10 years. If it's been around 50 years, conditionally it'll be 50 years. You see? So let's, that's my idea. There's one thing that's endangering the world today, which is something called the square area law. It's very simple. I don't know if it's a law. Everything called law usually is not law. But you know the Harry Potter effect, winner take all, taking place, ecology of the planet. The internet has caused crises to be we are more fat-tailed than before. You can see it in the data, incidentally. The density of the number of species per square meters is a lot higher in an island than in a continent. And it's actually proportional to the square of the surface of, if you have Eurasia versus if you have England. You get the idea? You have a lot more species per square meter in England. Before the tunnel, even now, you can't cross easily, they strip you. But so you get the point. So you should have more, I view the world, I don't like connectivity. Maybe people like it, it's nice, we're all here, but it's not good for stability. Flat world is not good for stability of the world. Flat world is unfair for writers because those who sell books on black birds, black swan that nobody understands can sell 2-3 million copies, you get the idea? Whereas normally, you should have, or the Harry Potter effects, millions, hundreds of millions of copies. You get the idea? Flat world causes more of these, what they call more fat tails.
Thank you.
In your book, you mentioned your surprise over, or the surprise over the war breaking out in the Levant region. I guess I saw many similarities between that and what is happening now in the whole Middle East. What suggestions would you have for the world community?
This is this is very hard to answer today here. Yeah. You get the point? That's so. All right, but so I won't answer except for saying the following. I was the other day on a plane. I'm saying last week on a plane, and I read The Economist about Libya. I'm saying Friday is what? This Friday? The previous Friday, The Economist. I was reading it last Thursday. Okay. The previous, as I say, Libya, remote, impossible. All right. I'm thinking within 10 days, look what happened. All right. So there, you see, the ability to forecast, even by the agents themselves, is close to zero. So when we're writing a paper in Foreign Affairs on that by saying that I call it the Obama error. He says he's blaming it on intelligence that they didn't see these events, as if intelligence, but even people involved can predict these events. You get the idea? So in a complex system with a lot of interdependence, incidentally, a complex system has one rule that to me is central. Why it generates fat tails is because central limit doesn't work, because one of the requirements of central limit is what? Independence. You don't have independence. If I buy a book and you buy a book, you don't have independence of observation, all right? So this interconnectedness is destroying independence. So it's making, you get random variables that peak go much higher and the other ones die. You get that dorm. So you have that the positive feedback effects that are monstrous. So that lowers unpredictability monstrously. We can say it's Extremistan, all right? But calibrating more is close to impossible.
You said that one of the solutions to solving the problems of small probabilities if we introduce the concept of meta-probabilities, so the probability of the
That's not what I said.
Oh, sorry.
I said the one reason to be cured of talking about small probabilities is if you start using meta-probabilities. You would then realize that number one, probability is higher than you think. Two, you won't know how high it is. You see?
Oh, okay.
Because a meta-probability has to have a meta-probability.
Yes,
so if you start having meta, you end up with, if I use, it's very simple. If I use a Gaussian with standard deviation, if I stochasticize the standard deviation, okay, using a log Gaussian, and stochasticize every time the degree of stochasticity, we call it VVOL. Is there an option trader here? We option traders, we say it's called volatility, and then volatility, and then volatility. You go dizzy, all right? Yes. You realize at least there's somewhere, some measures break down, others stay robust to it. You get the idea?
Yeah.
Events with probabilities above 25 and below 75 aren't affected like events estimated probability below. You get the idea?
Yeah. Okay, thank you.
But there's a curiosity of using probability, so you want something harder. It's called hard bounding rather than probabilistic bounding.
Yeah, comment on a question really. One thing, you mentioned something about doctors, where if you went to a doctor, you were more likely to get ill, for example. I would think that's...
I didn't say that. I said I was talking about the history of medicine between Menodotus of Nicomedia until penicillin Alexander Fleming. Or no, even then, 10 years after Alexander Fleming.
Exactly, but
Yeah.
going to a doctor, for example, wouldn't that be kind of obvious? The whole point of going to a doctor is that there is a problem. So obviously people who go to a doctor are more likely to die than people who don't, because people who don't go to doctors...
No, I'm definitely someone who looked at it is, would have, I mean, I think it's an elementary mistake, or it's conditional on going to a doctor. This is one regular Bayesian thing. That's not the point. The point is very simple. You look at the procedure versus non-procedure. If you bleed someone who has pneumonia, chance of death multiplied by 4. If you bleed someone who doesn't have pneumonia, all right, unconditionally, chance of death multiplied by 2. If you set foot in a hospital in Paris in 1870, chance of death multiplied by 4 merely by setting foot from hospital germs. You get the idea. If you give birth in a hospital in Vienna or Budapest or whatever it is, you know, from that story, then you're giving. Then you have all these what's it called? Puerperal fever, right? Versus giving birth at home and stuff like that. So this is how this was computed. Okay.
All right.
From the procedures, not from, because we don't have mortality data. But you're right. Normally, you have to think in a Bayesian terms.
All right.
Okay.
Wait, one other thing. The world is getting more connected, right? So
Yes.
no events really are independent. As you mentioned, me buying a book is no longer an independent event from you buying a book, even if I never meet you in my life, probably.
Yes. If you raise ranking on Amazon. of course,
Exactly.
yeah.
So, yeah, with things like that, do you expect these black swans, especially in the financial markets, to increase?
I don't
as
expect.
time goes on?
I've observed they have gone up, and I observed that if you put connectedness, then obviously the whole fat tail. You can see it from that island effect or from other arguments, or very simply from breakdown of independence argument. You see,
Okay.
but I'm not. I don't make expectation. I want a society not to have more or less black swan, but this is why I was disagreeing with Tony Blair. Tony Blair. No, what's the name of the other guy? Gordon Blair. Gordon Brown.
Gordon
right.
Brown. Yeah.
The other guy, but he's okay. Is these guys him and Greenspan wanted to eliminate boom and bust, and he said, no more boom and bust, thinking he understands economic life by tinkering with it. Instead of that, I want to say no. You want to have economic life has as many boom and bust as they want. I just want normal human beings to be immune from that. And what are the conditions? It's a unique form of society that can resist forecast error, can resist small probabilities, and rebuild a concept based on that. So I didn't realize by writing the Black Swans that I was writing just a mere, poorly confusing introduction to a much bigger problem, which is a problem of what I call robustness and fragility. What is fragile, what's not fragile at the macro level. So I got involved in all of that, and now I have to work for a living. Where I thought I'd finish the Black Swan, and then can relax. Now I have to go and start writing more stuff. You get the idea? So I'm working now on fragility. What are things that can withstand human error coming from perturbation of probability and stuff like that?
So the idea isn't to eliminate the black swans, it's to deal with them better.
Is to have system robust. Let me tell you exactly. Let me give you one hint. Mother Nature was at its modest, give 2 kidneys. And I'm sure for members of NYU Abu Dhabi is the system the case. No, you're born with 2 kidneys. People in Lebanon are born with 2 kidneys. Now, Mother Nature gave you that extra kidney. You agree? Having no kidney and borrowing them dialysis is debt. All right. 2 kidneys is redundancies. All right. Now, you no longer have to predict whether you're going to lose your kidney because of a virus, bacteria, which should be bacteria. Okay. Food poisoning, what's going to poison you. Trauma. Okay. Your cousin hitting you because you insulted them. All right. or a lion. You don't have to predict what event is going to meet. You have second kidney. So if I have money as under my mattress was gold and silver and this and that, I no longer have to predict whether it's Gaddafi who's going to take over, going to go invade Tunisia and go invade Egypt, or not invade anyone, or be invaded by the Maltese. I don't have to predict all these events. If I have an extra, you get the equivalent of an extra kidney. I can go sleep at night and let other people predict, mispredict, get in trouble, and stuff like that, and entertain themselves. You see the point? So this is why, based on that concept, you want to build a society that can withstand these shocks with these, things that don't predict, right? And that's it. And now I'm starting to see one measure that works beautifully as a heuristic, called it the fragility heuristic, in taking convexity of errors and forecasting, that sort of does solve two-thirds of the measurement problem.